So talking about aromatic, and what are the qualifications to be aromatic? There's a couple different things. You have to have, must be a planar. It must be planar. It must be flat at some level. So that means sp2 or sp hybridized. What else? It must be an uninterrupted. Interrupted pi system or p orbital system. Must be cyclic. Must be in a ring. And the number of electrons in the p orbital system needs to give a whole integer for the equation 4n plus 2 needs to equal the number of electrons in the p orbital system. The actual number of electrons in the p orbital system. That would qualify a molecule to be aromatic. If any one of those things isn't satisfied, it's non-aromatic. The only difference between aromatic and anti-aromatic, everything is exactly the same, except the one difference is the number of electrons in the p orbital system. In that case, it's 4n is equal to that. So you can start to kind of think about how many electrons need to be in these systems. So what I always do to remember, if I get lost, if I forget 4n plus 2 or 4n, I draw out benzene. And I'll remember benzene. And benzene's aromatic. And it has 6 electrons. So basically, do some quick math. Benzene only works for one of these equations. Minus 2, that's 4 equals 4n. So n equals 1. That's a whole integer. But for this other one, that's not a whole integer. And so that helps me remember, right? Benzene is aromatic. So that's always kind of a good bench point. So you can kind of figure it out, right? So 4 would be anti-aromatic. 8 would be anti-aromatic. 2 would be actually aromatic. Right? It'd work out. You get a 0 for a whole number, right? So just kind of be thinking about those numbers. Non-aromatic is everything else. So non-aromatic things, any one of these things are off, the being planar on uninterrupted system or not being in a ring, then most things are non-aromatic. So yeah, the 4n plus 2 is just an equation. So it just works out that that's like the sweet spot for the number of electrons in a ring in this system. There's no rhyme or reason. I mean, it's just the sweet spot for the certain number of electrons to be shared in the ring. Another way to kind of think of these, instead of if you don't want to memorize the equation or need the equation, for the aromatic system, it's always an odd number of pairs, of lone pairs or pi bonds. It's always odd. Or it's for anti-aromatic, it's always an even number of lone pairs or pi bonds in the p orbital system. Practicing some resonance structures. For this structure, it says it's an anion, so we know it has an overall negative charge. So it's an anion, so it's -1. And it wants us to add all non-bonding electrons and formal charges, and then start thinking about resonance structure. So usually, unless they say it, you can assume everything has a full octet. So then you got to go back and think about how many bonds do certain elements want to have. So oxygen wants to have how many bonds? 4. Oxygen wants to have 2. So it has 2. So for it to have a full octet, it would have 2 lone pairs. And that's neutral. How many bonds does nitrogen want to have? 3. But this nitrogen has 4. So it must have a plus charge, right? So it's using some of its electrons for another bond. Sulfur wants to have how many bonds normally? Where's sulfur at in the periodic table? Sulfur is it's 6 valence electrons. It's right below oxygen. So just like oxygen wants to have 2, but it only has 1. So that means it has an extra lone pair. So it has a negative charge. How many bonds does carbon want to have? 4. Here it has 3. So we must give it a extra lone pair to get to 8. And so now the carbon has what charge? A negative. So this is the first thing you got to get to starting this way. Right? So once you're here, you can do a couple different things for resonance structures. Let's start with the carbon with a negative charge. So let's move these electrons to make a new pi bond between the nitrogen and carbon, and we'll break the pi bond between the nitrogen and oxygen. Resonance structure arrows, resonance arrows. Right, remember in resonance structures we only move lone pairs and pi bond electrons. Never break sigma bonds. So this would give us a new pi bond. Nothing happened with the sulfur, so it still has a negative charge. And the oxygen got electrons, so now it has a negative charge. And who's still, so we still have to have overall net -1. So what are we missing here? Positive charge on the nitrogen. Excellent. Good? So that's one way you can go. The other way we could go would be, instead of having the carbon give electrons, what if the sulfur give electrons? So I'm just gonna redraw the initial compound, initial molecule. So that first one, we start with the carbon with the lone pair and the negative charge. And then this one, we're gonna start with the sulfur. Make a new pi bond between the sulfur and nitrogen. Lone pairs here still, of course. Plus charge here in the nitrogen. Electrons go up. Resonance arrow. Plus charge still in the nitrogen. That would be the other resonance form. Big mistake people forget. They'll forget the formal charges. They'll forget the lone pairs, which we've practiced quite a bit, but make sure you take care of that. So we have how many different types of resonance structures here? We have, right, A. These are both A. Call this one B and C. Which one of these is the most stable? Why B? Well, so there's still in the
carbon. I mean,
so the carbon doesn't have a negative charge there. That's good. So what's the difference, right? The biggest thing you gotta look at. So what's the same about all of them? The same about all of them, A, B, and C. Nitrogen has a plus charge. So that's not okay. So that's all the same. So that can't be different. What else is the same about? So one of them we have. It's where the negative charges are at, right? In A, you can have a sulfur and a carbon with a negative charge. In B, you can have a sulfur and oxygen with a negative charge. And in C, you can have an oxygen and a carbon with a negative charge. Which one do you think is going to be the lowest energy one? B. Why? That's right.
Well, because oxygen and sulfur are both really electronegative, so they're going to be holding the electrons anyway.
Right. So oxygen and sulfur, at least in relation to carbon, carbon with a negative charge is super reactive, right? That's not very likely to happen. So anytime a carbon has a negative charge, that would probably be the least likely resonance structure. A and C both have carbon with a negative charge. Go make that less likely. Excellent. Taking a look at another resonance kind of question. This one, it says there's 3 resonance structures of the following cation. So it's a cation, so it's overall has a plus charge, so it's a cation. One is given below, so we got one right here. But it's incomplete, so I think you got to add the plus charge, or the lone pairs. Add lone pairs, non-bonding electrons, and formal charges, and then draw the 2 remaining structures. This is the kind of one I would like to make sure, right, you can draw the structures in, but in your notebook you should draw out showing the arrows. Because what I'm going to ask you on a test or quiz is to draw the arrows. I'm not going to just ask you for the structure, right? So we have a plus charge. We should probably move electrons towards it. So a good numbering system here is key. So 1, 2, 3, 4, 5, 6. What electrons do we want to move? The pi bond between 2 and 3 would be the easiest one right now. Let's just do that. The pi bond between 2 and 3. So we'll take those 2 electrons, move them towards the carbocation, of course, right? So we broke the pi bond between 2 and 3. Where would there be a plus charge now? On carbon 3. New pi bond there. Plus charge here. 1, 2, 3, 4, 5, 6. Make sure we add in our lone pairs. What's the next resonance structure we'd want to draw? Lone pair between 3 and 4, so the oxygen lone pair is going to form a new pi bond again. Excellent. Notice what I always try to do is I always try to draw the stuff that never changed first, so I get that all right. The stuff that changes is where the work's being done, but I always try to draw the stuff that has never changed right away. New pi bond there. 1, 2, 3, 4, 5, 6. What am I missing?
Plus charge.
Plus charge on oxygen, and also there's still a lone pair on that oxygen too. Make sure you get that in there. Excellent. So now we have A, B, and C. And which one is the best structure? What's the best resonance structure? A, B, or C? C. Why? Well, oxygen is more electronegative, has a plus charge. Why is it? Why?
Octet rule on carbon.
The octet rule, right? If you look between A, B, and C, right? A and B still have carbocations that don't have full octets. And the first rule is the octet rule. C, right? Who cares that oxygen has a plus charge? Doesn't matter. Full octets. So C is the most likely contributor. These other ones are important, right? Resonance structures tell us how things react. So if you had to guess, where would a nucleophile attack? Where would a nucleophile end up on this structure? Which number? Where would nucleophiles end up? Got 2 options. If a nucleophile is coming in to react with this, because this is a cation, so I would consider this an electrophile, where would a nucleophile react with on this molecule? Which 2 places? Give me the numbers. Carbon 1, absolutely. And where else would it react? A nucleophile.
Carbon 3.
Carbon 3, absolutely. Why doesn't it attack the carbon? Why doesn't it attack the oxygen? Because is the oxygen electron deficient? Well, no, but we have a plus charge there. So what? Right? Lewis dot structures lie to us sometimes. So just because there's a plus charge doesn't mean that's really electron deficient. What this is telling us is carbon 3 is electron deficient. So that's why even though these resonance structures aren't as good, what do they tell us? They tell us something about how this is going to react with things. So that's the crucial thing to remember about resonance structures. They tell us about something about how something reacts. Right? Excellent. All right, we got this wicked large ring here. And it's asking us, determine the total number of pi electrons and the number of pi electrons delocalized in the ring. Indicate whether the compound is aromatic, non-aromatic, or anti-aromatic. Also assume the structure is planar. So it says right there, assume it's planar. Okay, so that tells us that's a check mark for aromaticity, right? Is it an uninterrupted pi system? Is everything sp2 or sp3 or sp2 or sp? So it's right. The whole thing's there's no sp. Basically, there's no sp3s around here, right? There is no sp3 around, so it's an uninterrupted pi system. First question says, what's the total number of pi electrons, and what's the total number of pi electrons that are delocalized in the p orbital system? So there's 2 different answers here. So we can couple it out a couple different ways. So let's just do the total number of pi electrons. How many are there? So I would say 2, 4, 6, 8, 10, 12, 14, 16. So there's 16 total pi electrons. But now be careful. How many total pi electrons are actually delocalized? They're all lined up in the same p orbital system. This is where this alkyne gets tricky. Don't forget the hybridization state of alkynes are sp. So it has 2 pi bonds, but are both those pi bonds delocalized in the system? No. That's the hard part here. So it'd be 1, 2, because the other pi bond is perpendicular, it's 90 degrees away from this p orbital system. 1, 2, 3, 4, 5, 6, 7. 7 times 2 is, there's actually 14 pi electrons that are actually delocalized or in conjugation, right? Or part of the p orbital system. So there's 14 electrons. So we can say 4n plus 2 equals 14. It's 12. 4n divided by 4. N is equal to 3. Molecule's planar. It's cyclic. Has an uninterrupted pi system. And has a whole integer for a 4n plus 2. This compound is aromatic. You could also look at it and say how many pairs of electrons are in the system, and it's 1, 2, 3, 4, 5, 6, 7. That's an odd number, also aromatic. This is this is remembering hybridization state in geometry, right? It all comes back to, right? We got to remember those things. Number 10, workshop number 1, is asking us to give the 2 starting materials that form this product. So we're talking about Diels-Alder. Hope you recognize that. So we need to draw the diene and dienophile that form this product. So this is a bicyclic system. So when we have the bicyclic systems, that means either the diene or dienophile came from a ring to start, because always in the Diels-Alder we make a ring. So if we make a bicyclic, that means we started with a ring and made a new ring, right? Hence bicyclic. So we need to number the carbons, figure it out. But also, when you do bicyclic, you also have the chance for the endo-exo type problem situation where, right, you can have something on the endo face, right, which is, this is the endo face. This is like, I would call this an endo product, right? It's similar to the axial product. And there's also the exo face. These are the exo positions. And so the hydrogen's here in the exo position. The interesting thing is, the endo product, right, where the stuff, the size hydrogen is pointed down, that's usually not the most stable product. But it comes from the most stable transition state. So we usually call the endo product is a kinetic product. It comes from the lowest energy transition state, even though it's not the most stable product. That may or may not matter here when we try to figure out what the start materials are, because that's really about how the start materials come together, but it's something worth talking about and thinking about. So which bond do we need to break? So always look for, you find the pi bond, and where the new pi bond is at, or where a pi bond is at, that is where the diene was. All right, so on the pi bond, that could be carbon 2 and 3, and that means this is 4 and 1 over here. All right, that's the diene. Right, the diene always has the pi bond at the end. That would make this the dienophile, 5 and 6. So we found that pi bond. That has to be carbon 2 and 3 of the diene, the 4 carbon piece. And it looks like that's also attached to, we'll call these 7 and 8. So the dienophile, we'll say, was 6 and 5 and 6. So 6 and 5. What was on 5 and 6? A methyl's on 5. And a ester. Were they on the same side or different side? So do we have a cis or trans dienophile?
Cis.
Cis. Everybody see that, hopefully? That you can see that they're both the methyl and the ester here are both on the endo position. So that means the alkene had to be cis. The dienophile had to be cis. Because the 2 H's then are right here. Good. What's the diene going to look like? Well, okay. We know, so plus the diene We know it has to be this basic structure, right? So that's 1, 2, 3, 4. Though we're missing 7 and 8. What's 8 bonded to?
6. Oh, wait, no.
That's a 1. 8's bonded to 1. So there's 8. 8's also bonded to 7, and 7's also bonded to 4. So those are your 2 starting materials here. Number those carbons. Right? So I always like to look for, right, you find that pi bond, and you break the 2 sigma bonds. That's kind of where you see those connections coming together. Right? So find that pi bond and work from there. Number those, and then that's part of the diene is part of the pi bond. Just make sure you don't lose stuff up here. That makes sense, right? This is a bicycle, so we had to start with a cyclic piece. So we started with a 6-member ring. There it is, and we made a new 6-member ring. So it makes sense. So if we're looking at just ethylene as a pi bond, what do its molecular orbitals look like? So we got to look and remember it's 1 pi bond. So it has 2 electrons, right? 2 electrons in each bond. 2 electrons. So it has, since it's just 1 bond, it has, its molecular orbital has 1 bonding interaction and then 1 anti-bonding interaction. So if you have a p orbital, you have 2 p orbitals. The way they come together to form a bond in a constructive manner to share electrons, they have to be in the same phase. So that's why they share electrons. So that would be considered a pi bond. And we put both of our electrons there. If this is our energy axis. If we had the same 2 p orbitals, but now their phases don't line up, so they're not able to share electrons, it's like 2 waves coming together but canceling out. So that creates a node. We call that pi star. It's an anti-bonding orbital, and its orbital is empty. Other terms, we call this the HOMO, the highest occupied molecular orbital. This would be the LUMO, lowest unoccupied molecular orbital. If you want to break a pi bond, what do? You put electrons in its LUMO. Right? It's pi star. If I want to break this pi bond, I put electrons in pi star. If you want to use a pi bond as a nucleophile, you use the electrons that are in the HOMO, the highest occupied molecular orbital. This is where it's most electron rich. This is where it acts like a nucleophile. So we use these electrons to form a new bond as a nucleophile. And so that's how we remember HOMOs and LUMOs. The LUMO piece of a molecular orbital is about a bond is its electrophilic part. The HOMO, the highest occupied molecular orbital, is its nucleophilic part. It's electron rich, electron deficient. But we need to know these things and the shapes of them and where they're at to understand how to make and break bonds.